We're standing at a fascinating crossroads in software engineering, wouldn't you say?
Absolutely. It feels like a real inflection point.
AI is automating tasks we once thought were, uniquely human. But what does that really mean for us, the people actually building the software? Is it a threat or maybe an incredible opportunity?
It's a profound shift, no doubt about it. And the central paradox of this new era is, well, it's quite interesting. As AI takes over the act of writing code, the value of understanding fundamental software engineering principles just absolutely skyrockets.
Mm,
The emphasis moves from mere code generation
right.
to critical code judgment.
So, okay, if AI is handling the typing, the mechanics, what do we need to master to stay ahead, to stay relevant?
That's the million-dollar question.
Today, we're diving deep into a curated stack of foundational books. And the idea is that these books hold the key to becoming an AI-leveraged expert rather than, an AI-reliant novice.
Exactly. It's about using AI as a tool, not a crutch.
Think of this as your shortcut, maybe, to understanding the indispensable judgment required. How to direct, critique, and shape AI-generated output into robust, high-quality software. We're on a mission, really, to explore why the future of code depends so heavily on the wisdom of the past.
It sounds counterintuitive, but it's true.
You're about to discover why these timeless principles are more relevant than ever for your career. Part 1. The bedrock principles of programming and computer systems.
The fundamentals.
To kick us off, we're starting with the absolute bedrock. Before you can effectively tell an AI to build anything complex, you really need to grasp the fundamental physics of computation, right?
You have to. You need that grounding.
This section is all about those foundational rules of programming and how computers actually execute instructions. First up, a book by the creator of C++ himself, Bjorn Stroustrup. It's programming. Principles and Practice Using C++. Now, this isn't just a language manual. It's a really deep dive into the principles of programming,
Yeah, it's much more than syntax.
focusing on writing useful, correct, maintainable, and efficient code through concepts like type safety and resource management.
And that's crucial because even as AI generates C++ code, it's often trained on this vast ocean of human-written code. Some of it's great.
But a lot of it probably isn't.
A lot of it is, well, mixed quality or outdated.
Mm.
This book teaches you modern C++ principles like RAII, resource acquisition, is initialization.
RAI.
Essentially, it's a C++ idiom. It makes sure resources, like memory or file handles, are automatically released when they're no longer needed. No leaks.
Okay.
It shows the why behind using things like std.uniqueCapturedPars, that's a smart pointer, that manages memory for you instead of raw pointers. Raw pointers are something an AI might frequently generate, leading to common issues like memory leaks and security vulnerabilities.
Right, the classic pitfalls.
And AI can certainly write the code, but this book gives you the wisdom, the judgment to make it trustworthy and secure.
But, I hear a lot of chatter, especially on social media, saying C++, it's too hard, it's outdated. AI can just write it for me now, so why bother?
Yeah, I've heard that too.
That feels like a dangerously short-sighted view to me.
It really is. C++ remains the backbone of high-performance computing. That includes the very AI frameworks and models we use every day.
So what happens if you rely on AI for critical C++ components without truly understanding its principles?
Well, it's like asking a translation app to write a legally binding contract.
Ooh, yeah. Bad idea.
It'll probably miss the critical nuance, maybe introduce catastrophic errors. In practice, you might prompt an AI, generate a C++ class that reads data from a network socket. Okay, fine. Then you, armed with Stroustrup's principles, perform what I'd call a principles-based code review.
Okay.
Does it use raw pointers? To refactor it with std.uniqueCaptr for RAII. Does it use generic void pointers? You refactor for type safety using templates.
Got it.
This transforms the AI from just a black box spitting out code into, well, a powerful, maybe junior pair programmer that you can effectively guide and correct.
That kind of knowledge creates a profound strategic advantage, doesn't it?
Absolutely.
While many will just use high-level languages to interact with AI APIs, you'll be able to work deeper down the stack, closer to the metal, building and optimizing the very infrastructure that powers AI. That, to me, is a career moat, something highly defensible against automation.
Couldn't agree more. It's about understanding the foundations.
Okay, next up we have a classic, often just called CS.app. It's Computer Systems, A Programmer's Perspective by Randall Bryant and David O'Halloran.
Ah, foundational text for sure.
This book really demystifies what happens under the hood when your program runs. It bridges that gap between high-level code and the actual underlying hardware. It's all about writing better software by deeply understanding the system's architecture.
Yeah, and when we think about the bigger picture, AI and ML models, they are incredibly computationally intensive programs, right?
Hugely intense.
And they're ultimately constrained by the hardware they run on. CSAPP provides you with the mental models to diagnose performance bottlenecks in those AI workloads.
Okay, like what specifically?
Well, for example, understanding the memory hierarchy, the different levels of memory from fast CPU caches down to slower main memory and data locality.
How close data is stored together.
Exactly. That understanding can lead to orders of magnitude performance improvements when you're training large models just by structuring data to maximize cache hits.
A cache hit, meaning the CPU finds the data it needs right there in its fast local memory.
Precisely. Avoids going to slower memory. Or, another thing, knowing about floating point arithmetic reveals how tiny, subtle rounding errors can sometimes cause model instability. That's critical in numerically heavy AI tasks.
Right. But the prevailing myth I often hear is, oh, my framework or my cloud provider, they abstract all the low-level stuff away, so I don't need to know it.
Yeah, that's a common one.
But abstractions aren't magic, are they? When an AI model trains inexplicably slowly, an AI code assistant isn't going to tell you, hey, your data loading pattern is causing excessive cache misses.
Exactly. It just doesn't have that physical context. Diagnosing and fixing that requires a human who understands that fundamental hardware-software interface. So, to apply this daily, imagine you're optimizing an ML data pipeline. You use an AI, maybe, to generate an initial Python script.
Okay, standard starting point.
But if it runs slowly, you use profilers, sure. But then you, with that CSAPP knowledge, you ask deeper questions. Is it compute bound, limited by the CPU speed? Or is it memory bound, limited by data access speed?
Hmm.
How is the data actually structured in memory? This leads to informed refactoring, like maybe using a column-oriented format like Apache Arrow for contiguous data storage. An AI lacking that physical hardware model wouldn't typically suggest that on its own.
So in an industry where AI model training and inference costs are a huge
A
concern,
primary concern, yeah.
the ability to optimize performance is a genuine superpower. It transforms you from just an AI model developer
Hmm.
into an AI systems performance engineer,
Sure.
making code run faster, cheaper.
It's a massive differentiator, especially as AI keeps driving more specialized hardware development. That expertise is gold.
Okay, moving on, we have The Practice of Programming by Brian Kernighan and Rob Pike.
Ah, legends. K&P.
Right. This book distills wisdom from these Unix pioneers, focusing on the craft of programming, writing code that's simple, clear, general, manageable, not just functional.
Yeah, and what's particularly insightful here, especially now with AI, is its focus on qualities that AI-generated code often, well, lacks.
Like simplicity and clarity.
Exactly. AI models optimized for functionally correct output, sure, but they have no intrinsic concept of elegance or readability. Their code can frequently be convoluted.
Hard to fault.
Very. This book champions clarity as fundamental. It gives you the toolkit to refactor and simplify that AI output, turning it from some opaque artifact into a genuinely maintainable asset. Principles like write clearly, don't be too clever. They're more relevant than ever when the machine you're working with is an AI that often prioritizes quantity or perceived performance over human comprehension.
But some might dismiss a book from 1999 with C examples as, outdated.
But the authors themselves explicitly teach universal engineering concepts independent of language. That's the key.
Right, and the idea that AI will handle this, it feels particularly weak here. AI can't generate a coherent style or design philosophy for a whole project, can it?
No, absolutely not. Without human guidance, an AI-assisted codebase just risks becoming this unmaintainable patchwork quilt of different styles and complexities.
Well, mess.
Precisely. Practically, this book guides that human-AI code quality partnership. Say an AI refactors a complex function for performance, but makes it totally unreadable. You, applying Kernighan and Pike's principles, can pause and ask, is this optimization really worth the loss of clarity? Is it actually faster in a meaningful way?
Good question.
Then you reprompt the AI. Okay, prioritize readability now. Use clear variable names. You act as the essential design taste, the judgment layer, and the book's methodical approach to debugging and testing. That's a powerful antidote to the often black box nature of AI-generated code.
So as AI inevitably increases the quantity of code in our system,
As it will.
the demand for engineers who can ensure its quality is just going to grow exponentially.
Faster.
Mastering these principles transforms you into the editor-in-chief of your team's codebase. You're capable of guiding both human and AI contributors toward excellence. This craft of programming, emphasizing judgment and simplicity, that feels like a deeply human skill AI can't replicate.
I agree. It's about taste and long-term thinking.
Next, we explore Elements of Programming by Alexander Stepanov and Paul McJones. This one treats programming as a really rigorous mathematical discipline, building high-performance code on abstract algebra. It's about deriving general abstract algorithms.
Yeah, Stepanov's work is profound. Its ultimate focus on correctness and generality is fascinating. See, AI models generate code based on statistical correlation patterns they've seen. That's different from mathematical axioms that guarantee correctness across all possible inputs.
Okay.
Stepanov's philosophy teaches you to think about algorithms in terms of their essential mathematical properties. For example, that a parallel reduction operation like summing all numbers in a big list is possible and safe because the underlying operation, addition in this case, is associative.
Meaning the order you group things doesn't matter, like A plus B plus C equals A plus B plus C.
Exactly. That mathematical property allows for parallelization. This abstract understanding ensures solutions aren't just empirically correct for the cases the AI saw, but provably correct and broadly applicable. He introduces concepts as these formal specifications of requirements for generic algorithms. It's much more rigorous than just describing what a function does informally.
But I can hear the criticism now. It's too theoretical, too mathematical for everyday programmers. Or even, AI could just generate the algorithm anyway. Does that really hold true, considering what you just said about guarantees?
Not at all. That misses the book's core point. Mathematical rigor isn't just academic. It's a powerful tool for writing better, more reliable code. AI operates on correlation. It can't prove why an algorithm works. It can't formally define the minimal requirements for any sorting algorithm to be correct. This book gives you the intellectual framework to define those requirements formally as concepts.
So even if you're not proving lemmas every day,
Right, you probably aren't. But the thinking process is transformative. When you're designing a generic library, maybe with AI assistance, you might prompt the AI for a function to find an element in some container. But guided by Stepanov's thinking, you then pause and ask, what is the most general concept this algorithm can actually operate on? Not just a specific std.vector, but maybe any readable range defined by iterators.
thinking more abstractly.
Exactly. You then refactor or reprompt the AI to be generic over iterator types, ensuring the resulting components are robust, reusable, and mathematically sound.
This mastery fundamentally changes how you see code. You move from thinking about just a series of steps to thinking about verifiable properties. That's the hallmark of a true software architect.
It really is.
This knowledge lets you design truly reusable APIs, contribute at a foundational level to core libraries, maybe even compilers, and lead technical direction with undeniable authority because you're reasoning from first principles.
That's the power of it.
Last, for this section, we have the definitive textbook on compiler construction, known everywhere as the Dragon Book. Compilers, Principles, Techniques, and Tools by Aho, Lam, Sethi, and Ullman.
The classic green dragon, purple dragon, depending on the edition.
Right. It gives this comprehensive overview of how source code gets translated into machine code.
So it's a great question. Why read a book about compilers now in the age of AI, especially with so many interpreted languages like Python being used?
Yeah, why bother?
The answer is that every single high-performance AML framework, whether it's TensorFlow, PyTorch, JAX, they all rely on their own sophisticated compilation stack internally. Understanding compiler principles gives you deep insight into how these frameworks actually achieve their incredible performance, from code optimization techniques like loop unrolling.
Doing more work per loop iteration.
Right. To the central concept of intermediate representations, or IRs. These are the abstract forms of code that compilers use internally before generating the final machine code. MLIR, for instance, is a modern multi-level IR used heavily in AI compilers today.
So knowing this helps you write better code even in Python.
Absolutely. An engineer who understands compiler principles can write Python or even JavaScript code that is JIT friendly, meaning it runs much faster because the just-in-time compiler can optimize it more effectively behind the scenes. You understand what patterns the compiler likes.
I could already hear some people saying, okay, but it's outdated or it's too theoretical because let's face it, most of us will never write a full compiler from scratch.
True, you probably won't.
So why invest that depth?
The value isn't necessarily in handwriting parsers, you're right. It's about understanding the underlying principles that make modern language runtimes work. Think about JavaScript's V8 engine with its JIT compilers. In your daily engineering, imagine optimizing an AI model for inference speed. You might use a specialized compiler tool like NVIDIA's Tensor. An engineer without compiler knowledge might just treat this as a complete black box. Press the button, hope for the best. But you, understanding Dragon Book principles, TensorArt is building a data flow graph internally and performing optimizations like operator fusion. That's where multiple small operations get combined into a single, more efficient one.
Ah,
So if the results after compilation are incorrect, you can intelligently debug the process. You might suspect issues related to floating point precision changes during fusion, or maybe the fusion itself went wrong rather than just being completely baffled.
that makes sense. It gives you a mental model for debugging.
Exactly.
This expertise positions you right at that crucial intersection of AI models, software frameworks, and hardware, the absolute epicenter of performance optimization.
It really does.
It opens doors to highly specialized and probably quite lucrative roles in AI compiler development, performance engineering, maybe even hardware accelerator co-design. While AI can certainly assist in writing code, compiling that code efficiently for all the diverse hardware out there, that's becoming more complex, not less, making this foundational knowledge critical and, I'd argue, enduring.
Couldn't agree more. It's a deep skill.
Part 2. Building at scale data, distributed systems, and performance.
Moving beyond the single machine now?
Exactly. This next section focuses on the monumental challenges of building systems that span many, many machines. Modern applications, and especially AI systems, are just defined by their relationship with vast, distributed, and constantly moving data. Our first deep dive here is into Martin Kleppmann's Designing Data-Intensive Applications, or DDIA. It's widely considered the guide to data systems.
Yeah, it's become a modern classic, essential reading.
It really deconstructs the architecture of things like databases, caches, message queues, focusing on those fundamental trade-offs you always face around reliability, scalability, and maintainability.
And when we connect this to the bigger picture, AI and ML systems are, well, they're the quintessential data-intensive applications, aren't they?
Absolutely. The scale is enormous.
They process these huge data sets for training. They need to access low latency feature stores for real-time inference. They manage complex data flow through MLOps, pipelines, machine learning operations.
Right.
DDIA gives you the architectural vocabulary, the mental models to design these systems robustly. Think about concepts like replication and partitioning for scaling training data across many machines, or understanding different consistency models, how data updates are viewed across a distributed system when you're tracking ML experiments reliably.
But I hear this prevalent myth, oh, this book is kind of obsolete now because of serverless platforms and managed data services. The argument is, the cloud handles all these complexities for you. How would you respond to that?
That's a really dangerous oversimplification. These services, they don't abstract away the fundamental principles and the trade-offs of distributed data systems.
They just give you different building blocks.
Exactly. A managed database still has a consistency model, like eventual consistency, where data might take some time to propagate everywhere. An engineer flying blind won't understand why their supposedly infinitely scalable database suddenly grinds to a halt.
Yeah.
Maybe it's because of a hot partition, where too much data or too many requests are hitting a single segment of that distributed database. DDIA teaches the timeless principles that govern all these tools, managed or not. It empowers you to be an intelligent architect, not just a consumer of services.
So how would you apply it?
Okay, imagine designing a real-time feature store for an ML model. You might prompt an AI for architecture ideas, Redis, Cassandra, maybe Postgres. fine.
Mm.
But using DDIA's mental models, you evaluate them not just as brand names, but as implementations of underlying principles. Redis offers great low latency, okay? But what are its trade-offs for durability if a server crashes? What about consistency? Cassandra gives you high availability, fantastic, but is eventual consistency acceptable for your critical features? The AI generates the what, the options, but DDIA provides the why and the framework for choosing.
Reading DDIA really accelerates your transition then, from maybe a back-end developer to a true systems architect.
I think so.
In an AI-driven world, this means being able to design planet-scale, real-time data infrastructure, not just, training a model in a Jupyter notebook somewhere.
Right, moving beyond the lab.
This expertise is immensely valuable and incredibly difficult to automate. An AI can generate components, sure, but it cannot perform that holistic, trade-off-driven reasoning required to design a complex, distributed system from the ground up.
That's the human architect's role.
Next, we look at software engineering at Google by Titus Winters, Tom Manschreck, and Hiram Wright. This offers a unique look into how Google approaches software engineering. They define it as programming integrated over time.
I love that definition. It emphasizes the long view.
It's about managing the challenges of building and maintaining a massive unified code base that's expected to last for decades.
And the enduring value of this book is its focus on exactly that. Long-term software sustainability at unprecedented scale. This is a problem that AI-generated code will inevitably exacerbate, not solve.
How so?
Well, AI dramatically increases the sheer volume of code, but it offers no inherent solutions for managing the resulting complexity over time. The principles in the Google book, like emphasizing rigorous code quality, comprehensive testing, static analysis, they become absolutely non-negotiable when you start integrating AI-generated code into your systems.
Right.
And concepts like Hiram's law.
Which states?
It basically says that with a sufficient number of users, every observable behavior of your system will be depended on by someone. This becomes critical as engineers start relying on AI-generated code that calls various libraries. If the AI subtly changes some behavior, even an undocumented one, it can break unforeseen dependencies downstream.
Ooh, scary. But I hear the misconception. These practices, they only apply at Google's massive scale. Is that fair?
Not really. The principles are universal. Problems of time and scale affect any project aiming to last more than a few months.
And what about the AI will solve this myth? How does that stack up here? Managing code bases over time.
It's quite naive, actually. AI can generate code snippets, sure, but it cannot manage a complex CI/CD pipeline. It can't design a fair and effective code review process. It can't decide on a sensible deprecation policy for an entire system.
These are socio-technical problems.
Exactly. They require human judgment, long-term perspective, negotiation, communication. Practically, this book gives you a blueprint for integrating AI tools responsibly. If your team starts using AI and maybe consistency or quality starts to drop, you can apply Google's principles. You might institute something like the Beyoncé rule.
The Beyoncé rule.
Yeah, the idea is that any AI-generated code, like Beyoncé, needs to put a ring on it, meaning it needs comprehensive unit and integration tests before it gets committed to the main branch.
I like that. Tests are the commitment.
Exactly. And code reviews must also focus strongly on style, simplicity, maintainability. You could use AI-powered static analysis tools to shift left, catching potential issues earlier in the development process, ideally even before a code review.
Understanding these principles really positions you as an engineering leader, doesn't it?
It does.
The most valuable engineers will be those who can think about the entire software lifecycle, from inception right through to maintenance over decades.
Yeah, the whole picture.
This book gives you the frameworks to lead those crucial conversations about technical debt, testing strategy, engineering productivity. It provides a clear path to leadership roles focused on building enduring systems and effective engineering cultures. That's a responsibility AI is nowhere near capable of assuming.
Not even close. It requires deep human insight.
Okay, our next deep dive is into site reliability engineering, how Google runs production systems, often just called the SRE book, by Betsy Beyer, Chris Jones, Jennifer Petoff, and Niall Richard Murphy.
Another foundational Google text.
It outlines SRE, this discipline pioneered at Google that treats operations as a software engineering problem, applying development principles to running highly reliable systems.
And this raises an important question. Why is SRE more critical than ever now with AI?
Yeah, why?
As AI models become integral parts of user-facing products, the reliability stops being just a technical concern. It becomes a critical business requirement. Downtime or bad predictions can be disastrous.
Right.
SRE provides a proven methodology for managing these complex, often probabilistic AI systems in production. It offers nuanced approaches like service-level objectives, or SLOs.
Defining measurable reliability targets.
Exactly. And error budgets, which quantify how much unreliability is acceptable. These help you balance pushing out new model improvements with maintaining production stability. For example, you might define an SLO for inference latency, say 99% of requests served under 100 milliseconds, or maybe for prediction accuracy, 95% correctness over a given period. SRE also emphasizes relentlessly automating toil, those manual, repetitive, automatable operational tasks in MLOps pipelines, and fostering blame-free postmortems when AI systems inevitably fail, so the focus is on learning and improving, not pointing fingers.
I sometimes hear people say, oh, SRE is just DevOps with a fancy name, or it's only for massive companies like Google. And then others claim AI will just automate operations anyway. What's your take on those?
Well, while SRE and DevOps definitely share goals, SRE is much more prescriptive and data-driven in its approach. As for AI automating operations, AI can be an incredibly powerful tool for SREs,
How so?
especially for things like anomaly detection and monitoring data. But it doesn't replace the human judgment needed to define meaningful SLOs in the first place, or to negotiate error budgets with product teams based on business needs, or to design resilient system architectures from first principles. Those require human insight and trade-off analysis.
So how does it work day to day?
Imagine you're managing a production ML service. You'd define measurable SLOs beyond just simple uptime. Maybe that 99% of inference requests are under 100 meters, or 95% model accuracy is maintained. You establish an error budget, the acceptable amount of unreliability for that SLO. Then you use monitoring tools, maybe AI-powered AI ops platforms, to track the service-level indicators, or SLIs. Those are the actual metrics measuring adherence to your SLOs.
Got it.
Now, if a new model deployment causes a rapid burn down of your error budget, an automated system, guided by your SRE principles, could trigger an automatic rollback to the previous stable version, minimizing user impact.
That makes sense. Automation guided by principles.
Exactly. As companies deploy AI in more mission-critical systems, the demand for engineers who can ensure reliability is going to explode. Expertise in SRE is the direct path to filling that need.
It transforms you into a systems engineer who can build and run innovative but also dependable services. You can lead MLOps initiatives, bridge that often difficult gap between data scientists and infrastructure teams,
That's a huge one.
and drive real business value by making data-driven decisions that carefully balance innovation with reliability.
That balance is key.
Okay, to wrap up this section, we're looking at a truly seminal collection of essays from way back in 1975, The Mythical Man Month by Frederick Brooks, Jr.
A cornerstone of software engineering literature, still relevant.
Absolutely. Its most famous thesis is Brooks's Law. Adding manpower to a late software project makes it later. It explores the inherent complexities of large-scale software projects, rooted in things like communication overhead and the need for conceptual integrity.
What's truly fascinating here is its profound relevance despite predating AI by decades. The book isn't really about specific technologies. It's about the human-centric challenges of collaborative creation.
And AI doesn't eliminate those.
No, it just reshapes them. Brooks's famous formula showing the quadratic growth of communication paths as team size increases, that's a timeless warning. And now it's potentially complicated by the idea of AI agents acting as team members, adding new complex communication channels we need to manage. And his argument for conceptual integrity in design, having a single coherent vision, that's a powerful counterargument to just building systems from a patchwork of disparate AI-generated snippets. It reinforces the absolute need for a strong human architect to provide coherence and vision.
The common misconception, though, is that it's outdated because it predates modern agile development or AI.
Yeah.
But isn't that missing the forest for the trees?
Completely. Its insights are about the fundamental nature of software development and human collaboration. Agile methodologies, in fact, are largely a response to the very problems Brooks identified back then.
Right.
And the idea that AI is somehow the silver bullet that Brooks famously said doesn't exist, That's a powerful modern myth we need to be wary of. AI is a powerful tool, a lead bullet maybe, but it doesn't eliminate the hard work of design, integration, testing, validation, especially for large, complex systems. Those remain fundamentally human tasks.
So how does this apply in daily engineering?
Okay, imagine a project is behind schedule. The default management instinct is often throw more people at it.
Classic reaction.
But a leader who's internalized Brooks resists this instinct. They recognize the added ramp-up time, the increased communication overhead. Instead, they might reevaluate the schedule realistically. They'd ensure the core architectural team remains small and focused on those conceptually difficult, indivisible problems. And then they might leverage AI strategically, maybe, to aggressively automate accidental complexity like generating unit tests or documentation, freeing up the human engineers for the essential design problems only they can solve.
Understanding these principles provides a real strategic advantage in project and engineering management.
Immense advantage.
It grounds you in the sober realities of what makes software projects succeed or fail. You can make better planning and staffing decisions, you can champion architectural integrity, and you can provide realistic leadership to non-technical stakeholders, building huge credibility.
Yeah.
As AI changes how code is written, the fundamental challenges of organizing human effort to build large systems, those remain, making this a timeless leadership skill.
Absolutely. It's about managing complexity, both technical and human.
Part 3. The human scale culture, teams, and reliability.
Shifting focus now.
Yeah, let's talk about the human element, because software is built by people, ultimately for people. Technology alone doesn't guarantee success. Often the way teams are structured, the culture they operate in, the processes they follow, those are the determining factors.
Couldn't agree more. The human systems are critical.
And these aspects are becoming even more critical as we start blending human intelligence with machine intelligence in our teams. Our first book in this section is by Intel's legendary CEO, Andy Grove, High Output Management.
Grove, a management classic, especially for engineers.
It's such a practical guide to management. His core idea is that a manager's output isn't their individual work, but the combined output of their team and the neighboring organizations they influence.
And what's so insightful here is its engineering-centric, very output-oriented approach in an AI-driven world where individual developer productivity gets highly augmented.
Yeah, the potential is huge.
The manager's role really shifts. It moves away from just tracking lines of code or tasks completed towards maximizing the leverage output of a combined human AI team. Grove's concept of managerial leverage is absolutely core here. A high leverage activity is one that generates high team output from relatively low managerial input or effort.
Give me an example.
Okay, teaching your team how to write effective prompts for an AI coding assistant, that's extremely high leverage. Or teaching them how to critically review AI-generated code based on principles. Also very high leverage. His principle of task-relevant maturity, or TRM, also applies perfectly. An AI might have high TRM for generating boilerplate code, it's mature at that task. But it has very low TRM for understanding nuanced business context or doing creative, out-of-the-box problem solving. The manager needs to assign tasks accordingly.
But I hear the criticism that a book from the 1980s about hardware manufacturing is outdated or irrelevant to modern software development. How do you respond to that?
I think that's a superficial reading, frankly. While the specific examples certainly differ, he talks about making breakfast, not deploying code, the underlying principles of process, leverage, output, measurement. They are timeless.
Right.
Software development, especially when you do it at scale, is fundamentally a production process. And the AI makes this a relevant argument. It's flawed. AI tools are force multipliers. They dramatically increase the potential leverage a good manager can apply. Grove's book is the definitive guide on how to think about and apply that leverage effectively.
So how would a manager apply this day to day?
Okay, consider team one-on-one meetings. An engineer mentions they're spending hours on repetitive debugging tasks. The manager, thinking in terms of managerial leverage, might suggest, hey, why don't you spend maybe 4 hours this week researching an AI-powered debugging tool, see if it could help. They frame it as an investment. If you spend 4 hours now exploring this, you could potentially save yourself and maybe others on the team 4 hours every week going forward.
That's leverage.
Exactly. The manager sets a clear output for that task. Deliver a demo and a recommendation next week. That single action leverages the manager's time to potentially increase the whole team's productivity. You can also use AI leverage to shift left, championing the adoption of AI-powered static analysis or code review tools to catch bugs earlier in the development cycle, saving time and effort later.
For any engineer who's aspiring to management, this feels like arguably the most important book they could read.
I'd agree. It's incredibly practical.
It provides such a clear, logical framework for thinking like an effective manager. In an AI-driven industry, the ultimate value of management is in designing and optimizing the system in which the work gets done.
Precisely.
You can use these principles to systematically increase team productivity, justify investments with data, and build high-performing, motivated teams where top talent, augmented by AI, can really thrive.
That's the goal.
Next up, Jim Collins' How the Mighty Fall, and why some companies never give in. This one explores why great, successful companies often decline and sometimes ultimately fail.
A sobering read, but essential.
He identifies 5 stages of decline, arguing it's usually self-inflicted, and that recovery is possible if you catch it before the final, irreversible stage 5.
And this book serves as such a crucial cautionary tale, especially today, as AI seems to be accelerating both the rise and the potential fall of companies. The pace is just incredible.
How do the stages apply?
Well, the 5 stages provide a diagnostic toolkit for leaders, but also for individual contributors. For instance, stage 1 is hubris born of success. This can easily strike a company that has a big AI breakthrough. They get arrogant, they stop listening, they stop learning.
Seen it happen.
Stage 2 is the undisciplined pursuit of more. Maybe fueled by AI hype, a company starts leaping into new domains where they have no deep understanding just because they can use AI there. Stage 3 is denial of risk and peril. This is when leaders start dismissing negative data, maybe about AI model performance limitations or ethical concerns, blaming external factors instead of facing internal flaws.
That sounds familiar.
Stage 4 is grasping for salvation. This is where a company in trouble lunges for a silver bullet, like a radical, unproven AI pivot, instead of returning to the disciplined hard work that made them successful in the first place.
I've heard the criticism, though, that this book is only really for CEOs or top executives. But aren't the signs of decline often visible much lower down, maybe to frontline engineers, even if they aren't leading the company?
Absolutely. Those signs often manifest first as things like mounting technical debt that leadership ignores, or maybe engineers raising concerns about AI reliability or safety that get brushed aside.
Right.
And the whole AI changes everything narrative. It's a dangerous fallacy here. AI is powerful, yes, but it doesn't make a company immune to arrogance, lack of discipline, or denial. In fact, AI's complexity and its sometimes black box nature can actually make it easier for leaders to fall into denial, blaming the AI itself instead of flawed strategy or inadequate human oversight.
So how can an engineer use this framework?
Okay, imagine a senior engineer dismisses a junior engineer's valid concern about the long-term maintenance cost of some complex AI-generated code, maybe saying, we're the best, we'll figure it out later. You, being familiar with Collins, recognize that as potential stage 1 hubris. You could then try to reframe the conversation to be more disciplined. Okay, but is this added complexity truly worth the potential performance gain? Let's apply our skills now to find a simpler, more maintainable design.
Challenging the hubris with data or principles.
Exactly. Or if leadership suddenly announces a splashy new AI initiative while the core product is struggling with bugs and reliability issues, you might identify that as potential stage 2 undisciplined pursuit. You can then ask clarifying, data-driven questions about resource allocation, staffing, and validation plans for this new venture.
Understanding organizational decline provides a powerful strategic perspective, even for individual contributors.
Yeah.
It allows you to identify healthy versus unhealthy environments, to become a voice of reason within your team, challenging hubris with data and discipline, maybe even help lead turnarounds if things go wrong.
Yeah.
In an industry with such rapid boom and bust cycles, especially around AI, recognizing these timeless patterns of success and failure is a profound strategic advantage for your career.
Knowing when to stay, when to go, how to influence, it's critical.
Up next, Clayton Christensen's classic, The Innovator's Dilemma. When new technologies cause great firms to fail.
Required reading for anyone in tech, I think.
It introduces the concept of disruptive innovation, arguing that great, well-managed companies often fail precisely because they do everything right for their existing profitable customers, which makes them vulnerable to initially inferior but eventually revolutionary new technologies.
And what's truly fascinating here is that AI isn't just one single technology. It feels like a catalyst for waves and waves of disruption across countless industries simultaneously.
Yeah, it's everywhere.
This book gives you essential mental models to navigate this chaos. It explains why your obviously better AI feature might get rejected by your current big customers, maybe because it doesn't serve their existing needs or workflows. And conversely, why a seemingly toy AI application from a tiny startup could eventually upend your entire industry.
Right.
It clearly differentiates sustaining innovation, which is making existing products better for existing customers, something large companies usually excel at, from disruptive innovation. Disruptive innovation often creates entirely new markets, frequently starting with simpler, cheaper, maybe good enough AI tools that initially look inferior but improve incredibly rapidly.
Now, a common misconception is just using the word disruptive as a synonym for any successful new technology. But Christensen's theory is much more specific than that, isn't it?
It is very specific. It's not just about being better, it's about being different, often simpler or cheaper, and serving an overlooked or new market segment initially.
And what about the idea that AI changes everything and somehow invalidates his dilemma? Does it?
Not at all. If anything, it makes the dilemma more acute, more dangerous. A large incumbent company might focus enormous resources on building massive, expensive foundation models, a form of sustaining innovation, making their existing AI capabilities better.
Okay.
Meanwhile, a nimble startup might create a small, highly specialized AI model that solves one niche problem incredibly well, maybe for a market the big guys ignore. That could be the disruptive wedge.
So how do you apply this day to day as an engineer or maybe a product manager?
Okay, imagine you're proposing a simple, maybe slightly rough AI-powered code analysis tool, perhaps for a niche programming language. Management might reject it, saying it's too small or it's not as powerful as our existing enterprise solution.
Classic big company response.
Right. But you, recognizing the innovator's dilemma, could reframe it. Look, this isn't meant to compete head-on. This is potentially a disruptive innovation targeting an underserved market of developers using this niche language. Let's create a small, autonomous team to test this hypothesis. The goal isn't immediate revenue, it's learning about a potentially new, growing developer segment.
Thinking differently about the metrics and goals.
Exactly. Or when you're evaluating new open source AI tools, you wouldn't just dismiss the ones that seem inferior today. Instead, you'd ask Christensen's questions. Does this enable new users who couldn't use the complex tools before? Is it significantly simpler or cheaper? Does it have a trajectory of rapid improvement that could make it dominant tomorrow?
Understanding the innovator's dilemma really transforms you from just a technologist into a strategist.
It gives you that strategic lens.
It equips you to effectively champion innovative projects within a larger organization, or maybe even to recognize opportunities to start your own company, providing a clearer roadmap for leveraging disruptive AI innovations.
Yeah.
This knowledge is absolutely essential for technical leadership roles, where evaluating emerging technologies and guiding long-term strategy is, well, pretty much the whole job.
It's table stakes at that level.
Okay, to close out part 3, we have Ben Horowitz's The Hard Thing About Hard Things. Building a business when there are no easy answers.
The brutally honest one, no punches pulled.
Exactly. It's this incredibly raw guide to the messy, painful, difficult challenges of running a startup, focusing heavily on what he calls the struggle and the need to make high-stakes decisions with incomplete, often ambiguous information.
And what makes this book so powerful, I think, is its unflinching focus on the psychological and emotional challenges of leadership. These are universal, but they often feel amplified in the incredibly fast-paced, high-pressure world of AI startups.
Yeah, the stakes feel high.
Horowitz's vivid description of the struggle, that feeling of self-doubt, maybe even despair that almost every founder or leader faces at some point, it's deeply validating, especially when a key AI model fails spectacularly or maybe funding suddenly runs out. His concept of peacetime CEO versus wartime CEO is also critical for the volatile AI industry. Knowing when to shift your leadership style from collaborative and consensus-driven peacetime to decisive command and control, wartime, is a crucial survival skill. And his principle of taking care of people, products, and profits in that order, that's paramount in a fiercely competitive AI talent market where people are your most valuable asset.
Now, a common misconception might be that this book is only for Silicon Valley CEOs building unicorns. But I'd argue the hard things, like giving really difficult feedback or managing underperformers or making painful trade-offs, those exist at every level of an organization, don't they?
Absolutely. They're universal leadership challenges.
And it's also sometimes criticized because it offers no simple formula, no easy answers.
But that's the entire point. There is no formula for the truly hard problems. Its value lies in providing a framework, shared experiences, and mental models for thinking through these incredibly difficult context-dependent decisions.
So how does this apply in daily engineering leadership?
Okay, imagine a key AI experiment fails badly, and team morale just plummets. You, as the leader, are now in the struggle, applying Horowitz's advice. First, tell it like it is. Address the team transparently. Okay, folks, the model failed. This is hard. That's exactly why we're the ones who need to solve it. Honesty builds trust.
Right.
Second, focus on the road, not the wall. Direct the team's energy away from blame or despair towards finding solutions. Maybe form specific task forces to investigate different aspects of the failure. And third, critically, manage your own psychology. You need to project calm and confidence to the team, even if you're churning inside. But find a trusted mentor, peer, or coach you can talk to honestly about your own struggles. Don't try to carry it all alone.
That's crucial.
And when hiring for your AI team, you'd follow his advice to hire for strength, not for the absence of weakness. Look for exceptional abilities in key areas rather than just well-roundedness.
For any technical professional who's aspiring to leadership in the AI space, this book feels essential.
Absolutely essential.
While AI can certainly help solve technical challenges, it cannot navigate the complex emotional and psychological landscape of leading a team through intense uncertainty and pressure.
No way.
Mastering these principles builds resilience, develops courageous decision-making, and helps create a high-performing culture where people feel safe to take risks. It transforms a great technologist into a great leader, a role that requires immense courage and emotional fortitude that AI simply cannot replicate.
It's the human element amplified.
Okay. Part 4. The Art of Influence, Human Dynamics, and Decision-Making.
Shifting gears again to the people side.
Yeah, because in software engineering, let's be honest, the best technical solution doesn't always win. Success often hinges on your ability to communicate effectively, to persuade stakeholders, negotiate trade-offs, build strong relationships.
Technical skills get you in the door, influence skills get things done.
Exactly. And as AI potentially handles more routine technical tasks, these so-called soft skills, they're rapidly becoming hard requirements for leadership and impact. Our first book in this section is by a former FBI hostage negotiator, Chris Voss. Never Split the Difference. Negotiating as if your life depended on it.
Such a great title and a fascinating read.
His premise is that negotiation is a deeply emotional process, not just a logical one. And he offers these psychologically grounded techniques to build rapport and influence outcomes.
And it's quite surprising, maybe, how universally applicable these skills are for the software engineers. You don't think of engineers as negotiators, but you are constantly.
Really? How so?
You're negotiating feature scope with product managers all the time. You're negotiating technical designs and approaches with your peers. You're negotiating deadlines and resources with management. It's nonstop.
Sure.
Voss's core method, what he calls tactical empathy, is about understanding your counterpart's mindset, their perspective, their underlying emotions, in order to gain trust. It's not about agreeing, it's about understanding. His calibrated questions, those open-ended how and what questions, are brilliant because they essentially make the other person solve your problem for you. They shift the dynamic from confrontation to collaborative problem solving. Questions like, how am I supposed to do that?
Puts the ball in their court.
Exactly. And even simple techniques like mirroring, just repeating the last few words someone says or labeling their emotions. It seems like you're concerned about the performance implications here, can de-escalate tension and build rapport surprisingly quickly.
But some might dismiss these as, manipulative tricks only for high-stakes hostage situations, or maybe think AI will handle negotiation simulations soon. What's your counter-argument there?
Well, the goal is absolutely not to trick people. It's genuinely about making them feel heard and understood. That builds trust, which allows you to arrive at better solutions for both sides. It's collaborative. And the AI will handle this idea. It's completely irrelevant here. Negotiation is a fundamentally human interaction based on emotions, psychology, nonverbal cues. An AI cannot read the frustration in a product manager's voice over Zoom. It can't build genuine, long-term working relationships based on trust.
So how does this play out in a typical engineering scenario?
Okay, picture a daily technical design debate. Two senior engineers are completely deadlocked on different approaches, maybe getting heated. A third engineer, acting as a facilitator, can use Voss's techniques. They might use labeling. Okay, it seems like you're very concerned about the long-term scalability if we go with option A and to the other person. And it sounds like you feel option B offers much better immediate performance.
Acknowledging both views.
Right. Then maybe mirroring. If someone says option A is just too complex, the facilitator mirrors too complex, encouraging them to elaborate beyond the label. Then, calibrated questions. How could we mitigate the scalability risks effectively if we decided to proceed with option B? Or what would need to be true for option A to feel simple enough? This shifts the focus from winning the argument to collaboratively solving the underlying concerns.
That's powerful.
Even when you're prompting an AI, you can use calibrated questions. What are the most memory-efficient ways you know to sort this data, and can you provide an example that clearly illustrates the trade-offs involved? Get the AI to work for you.
It really drives home that technical skill alone isn't enough to advance your career. The ability to negotiate, persuade, influence that separates a senior engineer from a true technical leader.
Big time.
And as AI automates more routine coding, the value of these human-centric skills just increases. You can use them to drive technical decisions, secure better projects, maybe even better compensation, and excel in leadership roles. It's about mastering conflict, de-escalation, trust building, guiding teams toward common goals.
It gives you a durable competitive advantage that's immune to automation. People skills matter.
Next, Robert Cialdini's influence. Psychology of Persuasion, another classic, this one on social psychology.
Yeah, Cialdini's work is foundational for understanding why people say yes.
It explores what he calls the weapons of automatic influence, these 6 universal principles like reciprocity, social proof, authority, liking, scarcity, commitment, consistency, which act as mental shortcuts in our decision-making.
And for a software engineer whose effectiveness relies so heavily on collaboration and teamwork, this book is absolutely essential reading. These principles are constantly at play, whether you realize it or not.
Where do you see them?
In code reviews, definitely. In design meetings. In presentations to leadership or other teams. Understanding these principles leads to far more effective communication and, well, influence.
Okay, give an example.
All right, when you're arguing for a particular technology choice, showing that it's a widely adopted industry standard, that many respected companies use it, that's leveraging social proof. It's incredibly powerful because people feel safer doing what others are doing.
Makes sense.
Establishing yourself as a credible expert on a topic, maybe through past successes or clear explanations, that builds authority, making others more likely to accept your recommendations. Getting agreement on a small initial principle first, we all agree we need a reliable system, right? Makes it easier to gain commitment for a larger action later, using commitment and consistency.
Now, a common criticism here is that it teaches manipulation. And again, some might think AI will make these human persuasion skills obsolete. Maybe AI bots will do the persuading.
Well, while the principles can certainly be used unethically, and Cialdini warns against that, his primary goal is actually to educate you so you can recognize when these tactics are being used on you and resist unwanted influence.
Defense as well as offense.
Exactly. For engineers, it's about framing your sound technical arguments compellingly and ethically, not faking expertise or tricking people. And the AI will make this obsolete argument. It holds no water whatsoever. These principles are deeply wired into human psychology. AI doesn't change the fact that humans are influenced by social proof or feel obligated by reciprocity.
If anything, AI might make understanding human psychology even more important.
I completely agree. As AI handles more analytical tasks, the truly human skills like empathy, persuasion, communication, relationship building, those become the primary differentiators. An AI can analyze code, but it cannot mentor a junior engineer through a tough problem, resolve interpersonal conflict between teammates, or inspire a team to rally around a difficult goal.
So how would you apply these principles, say, when advocating for a major code refactor? That's often a hard sell.
It is. Okay, you'd want to layer the principles. You'd use authority by presenting clear data on current bug rates, maintenance costs, maybe developer frustration levels. You'd leverage social proof by citing examples of other successful companies in your space who benefited from similar refactoring efforts. Maybe use reciprocity by offering a small, useful, automated tool first, something that helps with a piece of the problem, building goodwill.
Right.
Use commitment and consistency by getting everyone to agree on a shared value upfront. We all agree that our long-term goal is a reliable, maintainable, and efficient system, correct? Then show how the refactor supports that shared goal. You might even use scarcity by framing the decision in terms of a closing window of opportunity. If we don't tackle this technical debt now, it's only going to become exponentially harder and more expensive later.
Technical excellence is foundational, clearly, but the ability to influence is the accelerator for your career and impact.
It really is.
As AI automates more the coding, the value shifts to the how.
Yeah.
How do you get your good ideas implemented? How do you get buy-in?
Right.
Mastering these principles allows you to lead effectively, even without formal authority.
Yeah.
To be a more impactful tech lead or architect, to navigate organizational politics constructively. Ultimately, just to get more important stuff done.
It's about understanding and interacting with people, a deeply human capability that powerfully complements technical expertise.
Our next selection is maybe a bit unexpected. The most important thing illuminated. Uncommon Sense for the Thoughtful Investor by Howard Marks. It's an investment philosophy book.
Yeah, not a typical software engineering read, but incredibly valuable.
It's not about magic formulas or stock tips. It's about disciplined thought processes, emphasizing what he calls second-level thinking, understanding the difference between price and intrinsic value, and the paramount importance of controlling risk.
And what makes this book so surprisingly relevant is its direct application to making strategic technology decisions. The tech industry, and especially the AI space right now, is just characterized by intense hype cycles, FOMO, and significant uncertainty.
Totally. It's hard to see clearly sometimes.
Marx's principles cut through that noise beautifully. His most critical concept, second-level thinking, is about moving beyond simplistic surface-level views. First-level thinking says, AI is the future, invest everywhere, use the biggest model.
The obvious conclusion.
Right. Second-level thinking asks, okay, everyone knows AI is the future, so that optimism is already priced into the hype, the valuations, the competition for talent. What are the less obvious second-order effects of this trend? What risks are being ignored by the crowd? Which contrarian bet that goes against the grain might be overlooked but holds real potential?
It's deep.
That is the very essence of strategic technical leadership, thinking beyond the immediate hype.
Now, the most obvious misconception here is, this is a book about stocks. It's not relevant to me as an engineer. But that feels like a classic case of first-level thinking itself, doesn't it?
You've hit the nail on the head. It is a failure of first-level thinking to dismiss it like that. The book is about a philosophy for making high-stakes decisions under uncertainty in complex, dynamic systems. The stock market is just his primary domain, for example. The principles are universal.
And can AI really make these better decisions that Marx talks about? Does it do second-level thinking?
That's a great question. And Mark's work really challenges the narrative that AI will just make better decisions across the board. AI, especially current AI, struggles with qualitative, nuanced, second-level thinking. It struggles to assess things like long-term strategic vision or market psychology, or predicting non-consensus outcomes that depend on complex human factors.
Okay, so how does an engineer apply this thinking day to day? Maybe choosing a foundation model for a new AI product.
Perfect example. First-level thinking says, use the biggest, most famous, most capable foundation model because, well, everyone else is, and it's the best.
Right. Follow the herd.
But applying second-level thinking, you'd ask, okay, everyone's rushing to the biggest models. That means the costs are high, the competition for specialized expertise is fierce, maybe vendor lock-in is a bigger risk. What if a smaller, maybe open-source model is actually good enough for our specific application? It might have a much lower price in terms of cost, latency, ease of deployment, for potentially much better overall value for us.
Finding the inefficiency.
Exactly. Perhaps the real differentiator isn't the raw model size, but our ability to fine-tune a smaller model effectively on our unique proprietary data. That could be a contrarian bet. You'd also explicitly consider risk control, like avoiding vendor lock-in, maybe prototyping multiple options using different models, a portfolio approach, just as Marx advocates for investing.
Internalizing this philosophy really elevates you from just a technical implementer to the strategic thinker. That feels like a crucial leap for anyone aspiring to roles like CTO or VP of engineering.
It's a mandatory leap at that level.
You can navigate the inevitable hype cycles in the AI industry with more rationality, more skepticism. Make superior technology bets by focusing on the underlying value and risks, not just the surface buzz. Become a source of uncommon sense within your organization, challenging conventional wisdom constructively.
Yeah, being the voice of reason.
This is a form of wisdom of judgment that AI currently cannot automate, making it an invaluable, enduring asset for your career.
Deeply valuable.
Okay, finally in this section, we have perhaps the foundational text on interpersonal skills. Dale Carnegie's How to Win Friends and Influence People, first published way back in 1936.
The OG of people skills books still sells millions.
It really does. It provides these timeless principles for interacting effectively with others, rooted in things like showing genuine interest, avoiding criticism, and making others feel important.
And this raises an important question. Why is a book from 1936 still so crucial, maybe even more crucial in the AI era?
Yeah, why? Seems counterintuitive.
Because software engineering is fundamentally a collaborative team sport. Technical skills are only half the equation, maybe less than half sometimes. Your ability to work effectively with other people is what translates your technical prowess into actual results and impact. Principles like don't criticize, condemn, or complain. That's the golden rule for giving constructive code review feedback, right? Make it about the code, not the person.
Absolutely.
The only way to get the best of an argument is to avoid it. That's crucial for navigating technical debates constructively. It encourages you to genuinely try to see things from the other person's perspective before pushing your own. And the basics, building rapport through showing genuine interest in others, smiling, remembering names, these are timeless building blocks for trust within any team.
But some people criticize its advice as being common sense or maybe even manipulative flattery. And the ultimate misguided narrative I sometimes hear is that AI will make soft skills obsolete. What do you make of that?
Well, the book truly emphasizes sincerity. It's not about fake flattery. It's about making a genuine effort to understand, appreciate, and connect with others. The reason some of it seems like common sense is because it is foundational, but it's common sense that's surprisingly uncommon in practice, especially in high-pressure, sometimes ego-driven, technical environments.
True enough, we forget the basics.
And the AI will make soft skills obsolete narrative. That is perhaps the most misguided of all. As AI continues to automate more analytical and routine tasks, the deeply human skills like empathy, communication, collaboration, relationship building, influencing, they become the primary differentiators. They become more valuable, not less.
Yeah.
And AI can analyze code metrics, sure, but it cannot effectively mentor a junior engineer through their first big project crisis. It cannot resolve a brewing conflict between two team members. It cannot inspire a team to overcome a seemingly insurmountable challenge. That takes human connection.
So how can you weave Carnegie's principles into daily engineering work?
Okay, let's say a product manager proposes a feature that seems technically infeasible, maybe with a ridiculously tight deadline. Instead of starting with, no, that's impossible, you begin in a friendly way, talking in terms of their interests. Wow, I can see how this feature would be a huge win for our users. That's exciting.
Start positive.
Be a good listener first. Ask them to walk you through their vision, their goals for it. Then, maybe the most powerful principle. Try honestly to see things from the other person's point of view and let the other person feel the idea is theirs. So instead of directly saying your timeline is impossible, you ask collaborative questions that lead them towards that conclusion. Okay, given that we need to build a completely new data pipeline first to support this, which parts of the feature are the absolute most critical to deliver by the deadline so we can show valuable progress to the users?
Guiding them to the reality.
Exactly. It's much more effective. This book is a career accelerant, plain and simple. Technical skills get you in the door, but people skills are what enable you to lead projects, influence technical direction, build consensus, and advance into senior leadership roles.
Absolutely.
In an AI-driven industry, strong interpersonal skills make you a more effective collaborator, a better mentor, a leader who can bridge that crucial gap with non-technical stakeholders. As one engineer famously noted, the people skills are what makes someone shine. This book provides the foundational training for those essential differentiating human skills. It's the operating system for effective teamwork.
Okay, Part V, the Dragon's Hoard Mastering Complexity and Abstraction. Our final section.
Back to the deep tech.
Yeah, for our final section, we return to the core of computation. We're exploring books that offer profound perspectives on structuring code effectively, managing complexity, and optimizing performance at a deep level.
These are the texts that provide the intellectual tools to move beyond just being a user of systems
Right.
and become a creator of new abstractions, a true master of the complex machinery that powers advanced AI.
And we're actually revisiting the principles of the Dragon book here. Compilers, Principles, Techniques, and Tools by Aho, Lam, Sethi, and Ullman. Because it so perfectly bridges those foundational principles we discussed earlier with the mastery of complex modern systems, it really feels like a capstone to our technical collection.
I agree. Its enduring value is only magnified in the AI era because it teaches you how to think about and achieve performance optimizations in ways that an AI on its own can't fully grasp. It lacks the deep architectural understanding. Remember, every high-performance AI framework relies on sophisticated compilation techniques internally. Understanding compiler principles means you can identify why an AI model's performance is bottlenecked, often beyond what even an AI-powered profiler tool might tell you. You learn to write code that is JIT-friendly, optimized for just-in-time compilation. You understand concepts like operator fusion, where multiple small operations are combined for efficiency. And you grasp the critical role of intermediate representations, IRs, in modern AI compilers like MLIR.
So that myth we talked about earlier that it's too theoretical or outdated, that feels especially dangerous in the AI context now, doesn't it? It's clearly not just about handwriting parsers anymore.
No, absolutely not. It's about understanding the fundamental principles that make all these modern runtimes and frameworks work efficiently. An AI engineer who only knows how to tweak prompts or high-level framework settings without this foundational understanding, they'll be at a distinct disadvantage when it comes to deep system-level optimization.
Can you give that TensorRT example again?
Sure, you're optimizing an AI model for inference using NVIDIA's TensorRT. An engineer with Dragonbook principles understands that TensorRT isn't magic. It's building a data flow graph and performing precise optimizations like operator fusion. So, if the compiled model gives incorrect results, they can intelligently debug the compilation process itself. They might suspect issues related to flowing point precision changes during fusion, or maybe an incorrect fusion decision, rather than just treating the compiler as an opaque black box that either worked or didn't.
That debugging insight is key.
It is. You can also apply these principles to build better developer tools yourself, like static analyzers that truly understand code structure and can give much more intelligent feedback than simple pattern matchers.
This expertise uniquely positions you at that critical intersection of AI models, software frameworks, and the underlying hardware, the absolute epicenter of performance.
That's where the magic happens.
You can pursue roles in AI compiler development, deep performance engineering, maybe even hardware accelerator co-design. Roles that are deeply technical, highly valuable, and right at the forefront of innovation today.
And likely to remain so for a long time.
Okay, our next book is the standard textbook for information retrieval. Information Retrieval by Christopher Manning, Prohaka Raghavan, and Henrik Schutze.
Often called IIR, another foundational text.
It covers all those core concepts like Boolean search, vector space models, indexing strategies, evaluation metrics like precision, and recall the science of finding information within large collections of documents.
And this raises a really important question right now. Why is classic information retrieval, IR, still so critical in the age of large language models, LLMs? Haven't LLMs solved search?
Yeah, that's what you hear. Just talk to the AI.
Well, the most powerful and crucially the most reliable AI search systems being built today actually use a technique called retrieval augmented generation, or RA.
Raggy. Okay, what's that?
It's a hybrid approach. First, a classic IR system using principles from this book retrieves a set of potentially relevant documents from a knowledge base, which could be the web or internal company docs. Then, the LLM uses those retrieved documents as context to generate a coherent, informative answer. The IR part finds the facts, the LLM part synthesizes them into language.
Ah, okay. So the LLM doesn't do the searching itself.
Not in real time against specific document sets, generally no. This book provides the foundational knowledge for the critical retrieval part of RAG. The quality of the LLM's final answer depends entirely on the quality and relevance of the documents retrieved by the IR system first.
Garbage in, garbage out, basically.
Exactly. If the retrieval step fails, if it pulls irrelevant documents or misses the key ones, the LLM will either hallucinate an answer based on its generic training data, or it will simply say, I don't know, even if the information exists somewhere. Concepts from the book like term weighting, TF-IDF, vector similarity, cosine similarity, indexing, they are all core to making that retrieval step effective.
So that common myth, LLMs make classic search obsolete, you can just talk to the data now, that fundamentally misunderstands how these powerful generative AI search systems actually work under the hood, doesn't it?
It completely misunderstands it. LLMs don't search effectively in real time across vast arbitrary data sets. They generate text based on their massive but potentially outdated training data, or they simply lack knowledge of private, proprietary data.
Right.
RAG is the dominant solution for bridging that gap, for grounding LLMs in specific, up-to-date, or private information. And RAG explicitly relies on classic IR principles. This book describes the enabling technology for making LLMs truly useful and trustworthy in real-world search and question-answering applications.
So how does this apply day to day for an engineer working on, say, an AI chatbot?
Okay, imagine you're improving your RAG-based chatbot that keeps giving irrelevant or nonsensical answers. Your first instinct shouldn't be just to blame the LLM.
Debug the retrieval first.
Exactly. You first debug the retrieval component using IR principles. Are the right documents even being pulled for the LLM to use? You might analyze the queries, the indexing, the similarity metrics. Maybe you realize your system relies only on semantic vector search, which is great for conceptual similarity, but bad for specific keywords. Remembering the IIR book, you might implement a hybrid search approach, combining semantic search with traditional keyword search like BM25 for better overall relevance.
Best of both worlds.
Right. For ambiguous user queries, you might apply query expansion techniques, maybe even using the LLM itself to generate alternate phrasings of the user's question to improve the initial search. And critically, you'd use formal evaluation metrics from the book, like precision, recall, and F1 score, to systematically measure whether your changes are actually improving the retrieval quality.
As nearly every company seems to be building AI-powered search or Q&A features now.
It's a huge trend.
There's a massive demand for engineers who understand how to do it well. A deep understanding of information retrieval is the key differentiator.
It really is.
You can build state-of-the-art R8 systems, troubleshoot those complex AI search failures effectively, and lead the way in generative AI search applications. While many engineers can call an LLM API, you, mastering IR principles, can build the robust and reliable retrieval systems that make those LLMs truly powerful and useful.
That's a highly valuable skill right now.
Next up, Elements of Distributed Systems by Andrew Tannenbaum and Martin Van Steen. This provides a comprehensive introduction to the principles and architecture of distributed systems.
Tannenbaum, another giant in the field. His MIX operating system inspired Linux.
Right. The book covers collections of independent computers that need to appear to users as a single coherent system.
And understanding distributed systems is now absolutely fundamental for building any modern scalable software, but especially for large-scale AI systems which are inherently massively distributed.
How so?
Think about training today's huge language models. It requires coordinating potentially thousands of GPUs across a complex network. Serving those models to millions of users requires globally distributed inference infrastructure.
The scale is mind-boggling.
It is. This book gives you the timeless principles for reasoning about these incredibly complex systems. Concepts like transparency, making distributed resources appear local to the user or developer. Communication protocols between nodes. Consistency and replication, absolutely crucial for ensuring model updates or training data are correctly and reliably distributed. And fault tolerance, designing systems to gracefully handle the inevitable partial failures of nodes or networks without the whole thing collapsing.
But again, the common misconception. Cloud platforms make this knowledge unnecessary. The cloud handles all the distributed systems problems for me. Is that truly the case?
That is a dangerously tempting but ultimately false oversimplification. Cloud providers offer incredibly powerful building blocks. Yes, things like managed databases, load balancers, message queues.
But they don't design your system for you.
Exactly. They don't absolve the engineer of the responsibility of architecting a coherent, reliable, and scalable system using those blocks. An AI engineer just deploying models onto multiple cloud virtual machines without understanding distributed systems principles. They'll be completely unable to reason about potential failure modes or data consistency issues or performance bottlenecks that arise from the interactions between the components.
Right.
An AI assistant lacking this fundamental understanding of the laws of physics for distributed systems cannot solve these emergent system level problems. This book gives you those laws.
So how would you apply this when designing, say, a scalable AI inference service?
Okay, you need to serve millions of global users.
Mhm.
Guided by Tannenbaum's principles, you'd probably choose a client-server architecture, but with multiple replicas of your AI model running behind a sophisticated load balancer. You'd replicate those services across different geographical regions, maybe using cloud availability zones or regions, for both lower latency to users and better fault tolerance if one region has issues.
see.
You'd have to critically consider the consistency requirements for model updates. Do all users need to see the new model absolutely simultaneously? Strong consistency, which is hard. Or is it acceptable if updates propagate gradually? Eventual consistency. That's a key architectural trade-off. You'd explicitly design for fault tolerance. What happens if a server running your model crashes? The load balancer needs to detect that and redirect traffic seamlessly. And you design for scalability, probably using auto-scaling groups to automatically add or remove model replicas based on current load.
So even if an AI generates the Terraform script or Kubernetes config,
Right. Even if AI helps with the implementation details, this entire design process, making those architectural choices, understanding the trade-offs requires human judgment grounded in distributed systems principles.
expertise in distributed systems is clearly one of the most valuable and sought-after skills in tech today, especially in AI.
Without a doubt.
As AI models and the data they consume just keep growing, the complexity of the underlying infrastructure increases exponentially. If you have these skills, you can architect and build truly planet-scale AI systems. You can solve the hardest, most complex production problems, things like debugging race conditions across nodes or handling network partitions gracefully.
The really thorny issues.
And you can command a significant premium in the job market, leading to roles like staff engineer, distributed systems, or principal engineer, AI infrastructure. While AI can write code for one machine pretty well now, designing, building, and managing these global, resilient, scalable systems of machines for modern AI, that remains a deeply human and highly valuable discipline.
It's about orchestrating complexity.
And finally, our last book, Brendan Gregg's System Performance. This is the definitive, practical guide to analyzing and optimizing modern computer systems with a strong focus on Linux, which underlies so much infrastructure.
Gregg is the master of performance analysis tooling and methodology. His work is legendary.
It offers these holistic methodologies and a whole arsenal of tools for performance analysis, digging into everything from the hardware level right up to the operating system kernel and into the applications themselves.
And what's truly compelling here is its direct and immense value in the AI era. AI and ML workloads are among the most performance-intensive applications imaginable. They push every single component of a system, CPU, memory, network, storage, GPUs, to their absolute limits.
Right, they stress everything.
Achieving optimal performance and cost efficiency for AI training and inference. That's a critical business challenge for almost every company using AI today. While CSAPP gave us the theory of computer architecture, Gregg's book gives you the practical, hands-on methodology and the specific tooling for understanding how systems actually perform under load in the real world.
So it's the practice complementing the theory.
Exactly. You learn not just that a memory hierarchy exists, but how to use powerful tools like BPF, the Berkeley packet filter, which allows safe custom tracing in the Linux kernel to actually trace cache misses for a specific AI application running live in production. You can finally answer those tough questions. Why is my expensive GPU sitting idle half the time? Why is network latency so high between my distributed training nodes? Gregg gives you the methods to find out.
Now, a common misconception is that performance analysis is some kind of black art, requiring arcane knowledge. Or, maybe more recently, that new AI-powered observability tools will just solve everything automatically. I imagine it's more nuanced than that.
It absolutely is. While modern observability tools, some using AI, are fantastic for flagging anomalies, hey, CPU utilization spiked. They often don't replace the need for deep human understanding to find the root cause.
They tell you the what, not the why.
Precisely. An AI tool might say CPU utilization is high, but it usually can't tell you why. Is it inefficient application code? Is it contention within the operating system kernel? Is the system spending all its time context switching between processes? Greg's book teaches the methodical approach, like his USE method, to systematically drill down from a high-level symptom to the underlying root cause.
What's the USE method?
It stands for utilization, saturation, and errors. For every key system resource, CPU, memory, disk, network, you check its utilization. How busy is it? Its saturation, is there a queue forming? And if it's generating any errors. It's a systematic way to quickly identify potential bottlenecks. Relying solely on automated tools without this kind of methodical understanding is like seeing a warning light flash on your car dashboard, but having absolutely no idea how an engine actually works. You don't know where to even start looking.
So how would you apply this USE method to diagnosing a slow AI training job? Maybe one where the expensive GPUs seem underutilized.
Okay, great example. You'd apply the USE method systematically. Check GPU utilization, maybe it's low, like 50%. Okay, why? Then you check utilization, saturation, and errors for the other resources. CPU. Maybe the data loading and preprocessing cores are pegged at 100% utilization. Memory. Maybe memory bandwidth is saturated. Disk I/O. Maybe the storage system is saturated, with long queues, high saturation, trying to read the training data.
So the GPUs are starved for data.
Exactly. You've identified an I/O bottleneck as likely the root cause, not the GPUs themselves. Once you understand that, you can then use an AI assistant much more effectively. You can ask a target question like, okay, given an I/O-bound workload on a parallel file system, what are the most efficient file formats and data loading strategies to use in PyTorch to maximize throughput? Now the AI can give you relevant advice.
That makes perfect sense. Diagnosis first, then targeted remedy.
Precisely. Expertise in systems performance analysis is unfortunately rare, but incredibly valuable. In the world of AI, where single training runs can cost millions of dollars, an engineer who can methodically diagnose bottlenecks and shave, say, 20% off that training time, they provide a massive direct return on investment.
Huge ROI.
This skill is fundamentally about diagnosis, investigation, optimization, creative problem-solving activities that are inherently difficult to fully automate. While AI can certainly assist with data collection and maybe suggesting hypotheses, the deep holistic analysis connecting hardware, kernel, and application behavior within a complex production system, that remains a deeply human endeavor.
This positions you as the ultimate performance expert, a high-impact, high-visibility, and incredibly high-value role that will be in demand as long as we continue to push the boundaries of computation.
As long as performance matters, the skill will matter.
Okay, wow. That was a deep dive through foundational books.
It was quite a journey. But this deep dive into these foundational texts, I think it reveals a really powerful truth for engineers today. The rise of AI doesn't diminish the value of human expertise. It fundamentally redefines it. It actually places a premium on the very principles and skills these classic books champion.
So what does this all mean for you, our listener, trying to navigate this rapidly changing landscape? The AI paradox we mentioned at the start seems much clearer now.
Yeah.
As AI automates more of the mechanics of coding, it simultaneously elevates the importance of the skills it cannot easily replicate. Things like architectural vision, deep performance intuition, rigorous critical judgment, and empathetic, human-centric leadership.
Exactly. The professional who truly understands low-level computer workings, like from CSAPP or Greg's book, can diagnose AI model performance issues that the AI itself simply cannot comprehend because it lacks that physical grounding.
Right.
The leader who masters distributed systems principles, maybe from Tannenbaum or DDIA, can design the robust, scalable infrastructure that AI services absolutely need to function reliably. The manager who internalizes the principles of human dynamics and output, perhaps from Grove or Horowitz or Carnegie, can build the high-performing teams needed to turn AI's technological potential into actual business reality.
The future of software engineering, then, it isn't really a competition with machines, is it? It's much more about a partnership.
It has to be. Collaboration, augmentation.
And to be an effective partner in that collaboration, to be the architect, the strategist, the leader, the editor, you must possess that foundational knowledge. Knowledge that allows you to effectively guide, critique, validate, and shape the work of your powerful new AI tools.
Couldn't have said it better. This collection of books, maybe not every single one for every person, but the themes they represent, they form an essential curriculum for becoming that complete, well-rounded software professional in the AI era. They provide the timeless wisdom needed to build the future, not just with lines of code, but with judgment, with insight, and with a deep, enduring understanding of sound engineering principles.
So as we move forward, AI will undoubtedly give us incredible power to create, more than ever before.
The leverage is immense.
But it's you, the human engineer, the human leader, who will bring the purpose, the judgment, the vision, and the values to that creation. That's the ultimate deep dive, isn't it? Something for you to ponder long after this deep dive ends.